Welcome back, good morning. Recall from yesterday that we defined residual time as yt as Snt plus 1 minus t, age as t minus Snt, and duration x t as this y t plus z t, which is equal to S n t plus 1 minus S n t. Yesterday we were able to use essentially strong law of large numbers to work out the time average residual life, time average age and time average duration, right. We proved that for example, we proved that 1 over t, if you say in limit t tending to infinity integral 0 to t y tau d tau is equal to limit t tending to infinity 1 over t 0 to t z tau d tau, both are equal to second moment of the interval times over 2 x bar, right. This is almost surely, and we also showed from this is clear that t tending to infinity 1 over t integral 0 to t x tau d tau is expected x square over expected x almost surely, right. These are respectively the time average residual time, time average age and time average duration, right. Later, so these are time averages, right. So, later we will prove ensemble average version of this, namely that if you take a particular t, you take expected yt, yt is of course a random variable at any given time, right. After a long time expected yt is equal to, these are ensemble averages, equal to what answer do you expect? You expect the same answer, right. We will prove this later, okay, more involved. Now there is no almost surely, it is just numbers, right, and likewise. So, these are ensemble averages. So, these are time averages. So, for the ensemble average you are taking a very large time t. So, y t or z t or x t is a random variable, right. You look at a particular t, for example, x t is simply the duration S n t plus 1 minus S n t, the width of the interval that t is sitting in, right. The expected value of x t is of course a random variable for each t, right. See x t is a random variable for each t. So, you take its expectation and you send t to infinity, you get this number, okay. So, this is ensemble average, okay. You are averaging over various omegas, okay, as opposed to averaging over time, all right. Now, I pointed out yesterday that these residual time, age, duration, the expected value of these quantities is directly proportional to the second moment of the interval times, correct. So, if you have this x random variable, if it can take large values with some substantial probability, expected x square will become very large, right. So, typically the duration or the age or the residual time will be very large, okay. In fact, if you look at this quantity here, right, this guy, which is the expected or the average duration, it simply the width of the interval that t is sitting in, right. You are showing up to this, there is a bus process which is a renewal process, let us say, and you are showing up at some time t, right, and the inter arrival time of the buses in which you arrive, right, has expected value or time average expected x square over expected x. Is this bigger than expected x or smaller than expected x, or can you say something about this? See, what is the average inter bus arrival time if you have this renewal process of bus arrivals? Expected x, correct. Now, we are saying that if you come to the bus stop at some time t, the time duration between the previous bus and the next bus you will see is as expected value or time average value in this case expected x square over expected x. My question is this bigger on an average than expected x or smaller, or can you say something at all? So, how does this quantity compare to expected x? It is bigger, right. So, I am saying that this guy is bigger than, so whatever is here is bigger than or equal to expected x. Why? Variance is non-negative, right, or Jensen's inequality, x square is convex, right. Anyway, so the average duration of the interval in which you arrive to the bus stop is larger than a typical inter arrival time, correct. That is because it is a special duration which contains your arrival, right, and it tends to be therefore larger, it is statistically larger, right. So, these extraneous arrivals take place to the system when, or they are more likely to take place to the system where the inter arrival times are larger than usual, that is intuitively what we are saying, okay. Is that clear? Now, in this lecture we will generalize this sort of time average calculations to more general reward functions, okay. So, you can think of the residual time or the age or the duration to be some sort of a reward function associated with the renewal process. So, you can think of y t for example, at each time t you are accumulating a reward y t and you are looking at the time average reward or z t or x t for that matter, right. The only thing that is special about y t or x t or z t is that these are random variables, y t is a for every t y t is a random variable. These random variables depend only on things to do with that renewal duration. If you are at a time t, that reward y of t or z of t or whatever is only a function of whatever is happening in that renewal duration. It does not depend on previous renewals and renewals to come after and all that, okay. So, it turns out that everything we have done so far can be generalized to more general reward functions which are which depend only on things happening in that renewal interval, okay. So, let us talk about more general reward functions. So, I want to talk about r of t, right, reward function, okay. Let us say this is so this is a reward function, let us say it is non negative for now, it can be negative, but let us, to keep things simple, let us keep positive rewards, no losses. And what I want is that intuitively I want r of t only depends on, or maybe I should say depends only on the renewal interval to which t belongs. Okay. So, examples are r of t can be y of t, z of t, x of t, it can be some other functions thereof also, it can be z square t or plus y t whatever, right, can be anything that depends only on things happening in that renewal duration. Okay. So, in fact, we can the simplest way, simplest kind of a reward function is something that is, let us call this r tilde, something that depends on, it is only a function of z t and x t or y t and x t, it does not matter, right, because x t is, you can write any one of these two, I am just writing x t comma z t, okay, z t comma x t. So, this is one option, right. So, such an r of t would depend only on that particular renewal duration containing t, right, clear. So, this is one, this kind of a reward functions are certainly legitimate. I would like to stick to this form of reward function for now. We can in fact allow for reward functions which also depend on some independent source of randomness, which have nothing to do with the renewal process, for example. So, you could have coin tosses, you could have some other Poisson process which is independent of the renewal process, look at those Poisson arrivals during that renewal interval and all that is allowed, we will look at all that, but to fix ideas I want to look at r of t which is just a function of age and duration or age and residual time, okay, some function thereof. So, this could be some any nice function of z square t plus x square t or whatever, right. So, in this kind of a setting I want to calculate, so this is legitimate. So, I want to calculate what I want to calculate integral 0 to t r tau d tau. This is what, so this would be r tau, what we have done so far is we have taken r tau is equal to y tau or z tau or x tau, right, this is what I want, and the corresponding ensemble version would be expected r t, which we will do later, and you would expect that the answers to be the same. Okay. So, I want to state the main theorem which governs this time averages. This is called the Renewal Reward Theorem time average version. There is also Renewal Reward Theorem ensemble average version. Okay. This says that let r of t greater than or equal to 0 be a non-negative reward function associated with a renewal process with expected inter renewal time expectation of x, some x bar is finite. Okay. Let R n be the reward accumulated in the nth renewal interval. I.e. R n is equal to which is simply integral if each Rn is a random variable with expected Rn finite, then limit t tends to infinity 1 over t integral 0 to t r tau d tau equal to expected Rn over x bar almost surely. So, R of t is some reward function which is we have for fixing ideas we will take as some function of z t and x t, all right. We are assuming non negative, this is not essential, okay. This okay, we can even accommodate losses, reward and losses. Some R of t can take negative values, but what you want is that expected absolute value of R n should be finite, okay. So, we can this non negative is not such a key requirement. The key requirement is that R of t should only depend on that whatever the t is, look at the renewal interval, it should only depend on things happening in the renewal interval. We have fixed it to be R of x z t x t, but we can also later accommodate other independent randomness that is happening in that renewal interval, only in the renewal interval, okay. So, I want to calculate time average reward. What we are saying is that the time average reward is expected R n over x bar. Now, what is this expected R n is the question. What is this R n? R n is a random variable which is obtained by integrating your reward function. R of t is your reward function, right, R of tau, integrating that reward function here over that particular renewal interval, nth renewal interval, okay. Is that clear? So, it is a random variable, see Sn and Sn minus 1 are all themselves random variables. So, Rn is a random variable, and if Rn is expected value is finite, then the time average reward is equal to expected Rn over x bar almost surely. This is what the renewal reward theorem says, okay. This is quite a powerful theorem and it can be used to analyze queuing systems among other things. This Rn, so for example, when we took R tau equal to let us say residual time, right, Rn in that case was the area under the isosceles triangle, because we drew those triangles, remember, and the reward accumulated in one renewal duration in that case was simply x n square over 2, right. So, this Rn is generalizing the concept of that area under that particular renewal interval, that is really all it is doing, okay. So, x n square, so expected x square over 2 x bar you will get if R is simply age, right, you will recover what we derived earlier, okay. So, as you can imagine the proof will be very similar, you will upper bound and lower bound and use law of largeness, the strong law of large numbers, okay. Proof. So, we can write like this, right, we can do the same trick. This is true for all t, sum over n equals 1 to n t R n over t, right. I am basically doing the same trick, right. If you want to take 1 over t integral 0 to t, you are simply adding up. See, you are adding integral 0 to t r tau d tau is the sum of all the rewards obtained until t, right. That can also be calculated by adding all the rewards obtained in all the renewal intervals, right, until just before t and just after t. That is what the upper bound and the lower bounds are. So, you look at t, you look at the all the rewards accumulated till before the previous renewal, that is the lower bound, and till after the till just before the next renewal, that is the upper bound, right. Rn is the reward accumulated in each of these renewal intervals, correct. In the previous special case, Rn was simply xn square over 2, where the reward was just age, right. We are doing the same trick. Now, you send t to infinity, right, and you have to do some nt over divide by nt, multiply by nt, that trick has to be replayed again. So, you can write limit t tend to infinity Rn over n equals 1 to nt plus 1 Rn over nt plus 1 times nt plus 1 over t limit. So, there should be a limit. Okay. Now, what do you think we should do? So, these guys we already know how to handle, right. This guy we know, that guy we know, right. These guys go to 1 over x bar, strong law for renewal processes. So, what remains is to handle that bit and that bit, right. So, it looks like a sum of bunch of these Rn's divided by, it looks like a sample average of these Rn's, right. Now, the key issue is that these Rn's are IID, okay. Claim is that Rn remember was xn square over 2 in the previous example, right, which turned out to be if xi's are IID, xi squares over 2 are IID, right. So, claim these Rn's are IID, and that is because we have chosen the reward process to be dependent only on the renewal interval. So, the reward accumulated over one renewal interval will be independent of the reward accumulated over the next renewal interval, and they will be identically distributed. Okay. To see this, you can actually just write it out. So, if you have, so this Rn is nothing but integral Sn minus 1 to Sn r tilde, we have chosen this particular form, right, z tau x tau d tau. So, we have this is equal to, so remember that we call z of tau is equal to tau minus Sn minus 1, I am going from Sn minus 1 to Sn, right. So, z of tau will be tau minus Sn minus 1, correct. I am looking at the nth renewal interval, correct. So, this will be integral Sn minus 1 to Sn r tilde tau minus Sn minus 1 comma age will be Sn minus 1 minus Sn minus Sn minus 1, which is xn, correct. So, x tau, because this tau is sitting in Sn minus 1 to Sn, right. So, x tau will simply be that particular xn d tau, which you can rearrange by just a variable change to some z is equal to 0 to xn r tilde z comma x n d tau. Okay, what have I done? I have put tau minus S n minus 1 is equal to z, right. So, the integral will go from, now the z integral will go from 0 to S n minus 1, which is integral 0 to x n, correct, that is all that I have done. D, yeah, sorry, D I have changed the variable of integration, have I not? So, tau minus, so this I am putting as z, right. So, this should be dz, right, it is just a simple variable change. So, the z gets into z is a variable of integration, right. So, r tilde is a function of z and x n, and x get integrated out between 0 to x n. So, what comes out will only be a function of x n, correct. So, this r n will be a function of x n, some f of x n, like in our previous case r n was, previous example r n was simply x n square over 2, in general it is some function of x n, therefore, r n's are IID, right. So, this shows that this is only a function of, so this implies since x n's are IID, r n's are IID, okay. So, going back, so this will converge to what? This guy will almost surely converge to, see NT increases to infinity, right, almost surely. So, this will converge to expectation of R n, which is the expectation of R, so R n's are IID, so it will have some common expectation R, right, we can just write it as expectation of R n, no problem. It is not, it will not be a function of n, okay, it will be a number, all right. And this guy will converge to, so this guy we know already, right, this guy converges almost surely to 1 over x bar, this is also going to 1 over x bar almost surely, this will go to the same limit, right, this will also go to, goes to expected R n or expected R, right. So, this whole so what I want to say is that, so maybe I should, I do not need such big an arrow, so I should just say this guy goes to almost surely to expected R n. So, we can easily see therefore that limit t tending to infinity 1 over t integral 0 to t r tau d tau is almost surely equal to expected R n over expected x. Same logic, okay, nothing changes from what we did for x residual time or age, except this R could be more general, all right. Ideally, I would prefer to write expected R n as expected R, because R n's are IID, so they have a common expectation, right, but Gallagher maintains the n, so I am keeping the n, but please note that expected R n is not, is common across all these n's, it will be a number, okay. See, because the left side has no n, right, if you think about it, left side is just a number, right, for each realization you get a number of the process, right? Each realization of the stochastic process you will get some number. So, the left hand side is a random variable really, right, but the left hand side does not have n. So, the right hand side really should not have n, and it does not, it appears that it has an n, but expected R n is the same for all n, because R n's are IID, right. So, the almost sure limit of the sequence of random variables is this number, that is what we are saying, okay. Now, this has many applications, okay.